is also an a over b power, right? Because we can write it as e to the b to the a over b. So since s sub a over b is a over b power free, it's also a power free because every a power is an a over b power. But s of a is the lexicographically least a power free word. So therefore, it's lexicographically earlier than s a over b. So that's one direction. The other direction, you show that s a over b is lexicographically less than or equal to s over a, and so these sequences have to be equal. So this is really nice. It cuts down all the rational numbers to this, very small interval where there's only infinitely many rational numbers between 1 and 2.
Sorry. Were you using like a over b being greater than 2 here in the proof?
The other direction.
Oh, the other direction. Okay.
Yeah. Maybe.
Okay.
Yeah, that's a good question. It's probably in the other direction.
Well, we did it for cubes, right? We were avoiding cubes in the 3.5.
Right.
Exactly. Yeah.
All right. So we only it suffices to look at rationals between 1 and 2. So here's a rational between 1 and 2.
What?
That isn't.
Oh, 5 there. Sorry.
Oh yeah. 5.
I thought it was the picture. I'm sorry. Okay.
So here's the first few terms of the sequence, and here's the sequence partitioned into columns of width 100. And so I'm going to switch now to Mathematica, and
Oh yes, good. The width button.
yeah. So here's a dynamic thing that I've set up that basically lets you just change the width. And we found
Hey!
105. But maybe 105 isn't the minimal one. Maybe 105 is a multiple of the smallest one.
That's right.
So we should go backwards actually too. So we're getting closer. Okay, so 98 also seems to do something.
Let's try 7.
All right, let's try 7.
Oh snap!
All right.
Okay, it's a little hard to tell. Try 14.
Can we zoom in?
Yeah.
I like 7.
Yeah.
That's so much white space, right?
7's gotta work.
Yes, 7 works. It's just
The white space is meaningful, right? It's not just like.
Yeah. So here are the boundaries. So that the white space on the left is meaningful. The
And-
white space on the right isn't.
Oh, okay.
But yeah, 7 is the right answer. So here's that picture.
Great graphic.
And here's the theorem. So not only is 7 the right answer, but we also have a morphism. So this is really similar to the morphism for S sub 7, but we have a 1 here instead of a 0. So this sequence is the fixed point of this morphism. Okay, so what does 7 uniform mean? 7 uniform just means that this is length 7. And it follows that this is a 7 regular sequence. So 7 is the right number for 5/3. All right. What about 8/5? So again, here's the word partitioned into the sequence partitioned into rows of width 100. You see the answer there when I changed the. Maybe you didn't see it. All right. So here's 100 again, and again you can sort of slide through. Let me make this bigger.
Yeah.
I don't want to make it too big because I know the answer. So sometimes you see things start to align pretty well, but then they don't work. Then you keep going, and then you lose it, and then something comes back, and then you lose that. So let's go farther out here. So I spent a lot of time actually doing exactly that.
Again, like just visually.
Yeah, just visually.
That's pretty good.
Program it to recognize.
Yeah, so what you can do is, so these dark spots are high numbers. This might be 4 or something. And so you can look for all the positions of 4s and look at the differences between the consecutive positions where the 4s occur, and then take the GCD or something like that. And that gives you a way to guess Okay, that looks better. Let's see if we go down here.
But
Okay, we're really close.
Oh.
And then it snaps together.
Do we really have to go that far?
So 733, we can look at the factors of 733. So it's a prime. So yes, we really have to go that far. But what we get is, so we get 732 columns, and then in the very last column, we get the sequence appearing in a self-similar way. At least it fits on a slide, right? So here's the morphism.
For 8 fifths. Okay, yeah. That is not 8 times 5.
Are you sure?
Not 8 times 5. So the right answer is 733. Here's a 733 uniform morphism that ends in n plus 2 that shifts. So yeah, that generates this sequence. 13/8 steps.
Yeah, exactly. 13/8. Yeah.
Yeah. Actually,
You're
early on. I did think there was something going on with Fibonacci ratios.
There's not.
It didn't turn out to be the case. Oh, we'll get to that. We'll get to that. All right. I just want to show you one more. All right. Here's 7/4. Let's see. Do I even have a picture for 7/4?
I love this game.
It's great. So some of these, I computed like 100,000 terms of these, and it takes a while because to add one term, you might have to check sort of arbitrarily far back, right? So it can take a while to compute terms. So I computed 100,000 terms of the sequence, and my visual checks didn't find anything, and the automated checks didn't find anything. So I computed 100,000 more, and let's see, did I lose my talk? I computed 100,000 more and still nothing, and computed 100, and then I was meanwhile looking at a whole bunch of these rationals. So I ended up looking at about 900 different rationals in the interval 1 to 2. So I was computing, and a lot of them I was finding structure for. So I just, okay, forget about 7/4 for now, and then I would come back to it, and then eventually I don't know how many terms I computed, but the right number is 50,847. And so what this picture is, I'm line wrapping the line wraps now, because this is, otherwise it'd just be way too long. So there's a 50,847 uniform morphisms. So this word "u" has like 50,846. It's just a word on I forget what the alphabet is, 0 through 2 or something, and then n plus 2. And this is a theorem. So we've proved these, not by hand, as you can imagine. I'll say a little bit how I proved them, but I just want to show you some other things that happen. So here's one. Here's 6/5. Here you only need 1,001 columns, but something strange happens, which is that there's a transient period. There's a transient portion before it sort of falls into these nice columns. So and the self-similar column is right here. It's not the very last column. So you get a bunch of constant columns, and then self-similar behavior happens somewhere else because this transient sort of, I don't know, it takes a while to sort of work itself out or something. So to deal with this transient, we can still write this as in the morphism language, but we have to introduce a new letter, 0 prime, that sort of encodes the transient. And then we have this coding that sends 0 prime to 0 at the very end, and leaves all the integers the same. So there exist two words u and v of these lengths. So this is the transient length basically, such that when we have so we do something special for 0 prime. We have to stick on this transient, and then we apply v to 0. And so what this means is that the self-similar column also contains the entire transient again. It's not just like once we get here we start with this whole nice sequence shifted up. This transient, the self-similar column actually contains the entire transient from the beginning. So the transient is sort of an intrinsic part of this sequence. And lest you think that we were able to identify structure in all of these, here's one where we don't know the structure of, even conjecturally. So for 5/4, when you break it into columns that are 144 columns, you get a lot of sequences, a lot of columns that seem to be stable, seem to stabilize to a constant column or periodic columns maybe. But no matter how hard I tried, I wasn't able to find the right width that would really show the structure of the sequence. So I don't know what the structure of the sequence is. So here's sort of a catalog of the ones we've looked at so far. So it's this really bizarre function from rational numbers between 1 and 2 to positive integers that sort of describe what positive integer is this sequence reflecting the base case structure of. It's a kind of a bizarre function. So and we don't even know whether there is always a k. So for 5/4, for example, it would be nice to know whether these sequences are always k regular for some k, and if they are, how are they related? How is k related to a over b? So here's a family. This doesn't have 13/8 in it, but basically some of them come in families, right? So all these look very similar when you partition them at their correct width. And so it's something like this that we can say, well, once you've seen 5 or 10 of these, and they all look the same, you write down the morphisms, and then you can pretty quickly guess sort of a general form for them. So here's the first theorem that didn't just apply to a single morphism, a single word, a single sequence, but it applies to a whole family of sequences. So every rational number in the interval 5/3 to 2 with an odd denominator, we have a morphism that looks like this. So the basically of 0, the run lengths of these strings are linear combinations of A and B, and so that was sort of a hint that maybe we should be looking at morphisms with linear combinations. The lengths of zeros and whatnot are linear combinations of A and B, and this is basically all the other results that we have, all the other symbolic results like this one that apply to a whole family of morphisms. They were of this form, so they have lengths that are symbolic in linear combinations of A and B. So, again, to prove something like this, we have to show that the morphism preserves A over B power freeness, which means that if a word is A over B power free, then when you apply a morphism to it, you get another A over B power free word. And if you have that, then since 0 is A over B power free, then it follows that the infinite word is A over B power free. But that's just one step, because then you also have to show that the sequence is lexicographically at least. Yeah.
So does this really mean that we only care about the interval from 1 to 5/3 now?
No, well,
No.
because there's some even denominator.
Oh, right,
Like
yeah,
3/4 or
but-
something.
Yeah.
Would it help
to use non-uniform morphisms, or is that
7/4.
I don't know. None jumped out at me, but maybe I wasn't looking for them. Yeah.
Did you look at? So it looks like B being odd is special. How about B is twice an odd or something? Did you look at something like that?
We did so we had 900 rational. We have data for 900 rationals. For about 450 of them, I could guess like what the right k value is, and so then I tried to guess. Here's a bunch of data. Which k's are which linear combinations of A and B, basically, right? Because if you have a bunch of k's that are all 5a minus 4b for their rationals, then maybe there's a family there. And so this is how we got these families. So I think it would have come up there.
You cannot teach the computer to do everything?
Yeah, you can. Most everything. So and in the end we found 30 symbolic morphisms, parameters in A and B. So these theorems are just that these are A over B power free morphisms. So not all of the transients are sort of another issue. But showing that morphisms are A over B power free, we were able to do completely automatically. And this is sort of the general form that the theorems take. So you have some interval, you have a couple excluded rationals, and they come up because when you have these run lengths that are symbolic in A over B, you're sliding windows, and you need to know whether you're entering this this window or not. And so you're comparing two things that look like this, and you want to know which one's greater on an interval. And if one's greater than the other on some portion of the interval, but then they switch, then you have to break the interval into two subintervals, and then you get an endpoint that you have to test at in the middle. And maybe that endpoint maybe just doesn't work. maybe, and if you go back, so you can discover these things by trying to prove it, and then when you go back and actually look at the word, you see that, oh yeah, that word actually doesn't fit in this family at all. So it's kind of interesting. Here's the longest theorem in the paper. So this morphism has 279 non-zero letters. It's a 67A minus 30B uniform morphism. It works for all B's relatively prime to 67. All denominators relatively prime to 67. So yeah, and that's another condition that comes up in the proof. So to do these things computationally, we had to optimize a lot because you have to do a lot of checking, and so we wanted to, we really have to optimize, and so this one takes about 7 hours to prove, I think, of computer time. So here's the coverage of the morphisms we have. So near 1, we have very few morphisms. Near 2, we have, the larger you are, the easier it is to sort of find an A over B power-free morphism. Let's see what else I want to say. So here's a family with a transient. This was sort of an extra layer of complexity, but we were able to prove these symbolically also. And there were some rational numbers that don't seem to belong to families, or at least that we were able to find. But the proof techniques work the same. So we can still prove them. So 7/4 took about 6 hours to prove, I think, because again you have to sort of cycle, check that all these sort of things work out for the morphism. And it'd be really nice to understand these values somehow, but I don't know how. And then finally, this word, this was a big surprise. So here the self-similar column turns out to have zeros interspersed with the other terms. And so what it means is that here's the recurrence. So this isn't the original sequence isn't shifted up by anything. It's actually the original sequence, which means that this sequence for 27/23, this is a sequence on a finite alphabet. So we started off, saying, okay, we're going to forget about finite alphabets because infinite alphabets are easier. But it turns out that even for some sequences, the lexicographically least sequence on the non-negative integers actually only uses 3 letters.
Is that the smallest
This
example?
is the smallest example that we found. I mean, we have a couple others, but I think this is the simplest one. So I'll stop there. Thanks very much.
In time for a quick question?
So it seems like things that influence the structure of these is probably the actual number of that ratio is probably the A over B, what that is on a number line, if it's big or small, and maybe something like the number theory, something such like how divisible are things.
Yeah.
So that's like maybe a cube divided by a prime that's not too far away. Do you suspect if we took 7 cubed divided by a prime that's close to the... No?
I don't know. Maybe. I mean, I don't think it's that sensitive to the... I think it's more sensitive to the location on the number line than to the actual divisibility. I mean, there are some divisibility conditions on the denominator for these families. But yeah, so I mean, this one, I don't know if it belongs to a general family.
Thank you very much.
Thanks.
We should just ask a question in private. Thank you for dinner.